Gentlemen, today's first demonstration will be given by Nancy Hardwick, CEO of MELD Manufacturing Corporation. The topic of demonstration is Battlefield Deployable Additive Manufacturing Technology. The company will have 20 minutes to demonstrate their technology, followed by a 10-minute Q&A session. And when you're ready to begin, we will start the clock.
10, 9. Good morning, I'm Nancy Hardwick from MELD Manufacturing Corporation. It's an honor to be here. I'm very excited to share with you all that we've done. We came to the competition focused on building and repair in support of next-gen combat vehicle, but our customer discovery led to new applications, and so today I'll share the demonstrations that we did in support of our original white paper and then some additional demonstrations that we've done. First, I want to go over what MELD is. You can think of MELD as a 3D printer for metal. It's very unique because we don't melt the metal. This is a very unique additive manufacturing or metal deposition process. The rotation and force of material through this tool puts energy into the metal, allowing it to be moved, again, without melting. You see it flowing, but it is not a liquid at this stage. And we're also able to move the material underneath. So we literally stir the two together and create a wrought, fully dense product. This no-melt process is disruptive because it shatters many limitations. It shatters the limitations of materials, it shatters the limitations on size, and it shatters limitations on form of metal that can be put in the machine. It's a little twist on a 30-year-old process. So our first demonstrations will focus on building and repair, and very importantly, at the point of need, in addition to in the factory or at a depot. We wanted to build a component that would contribute to the lightweighting goals, primarily of NCV. So our first demonstration focuses on weight savings and cost per unit savings in manufacturing, and you'll see we also contribute to the goals of sustainment while enabling the use of advanced materials. Our focus at first is on the turret basket in a tank. This is a very large component consisting of a floor, which can be 7 to 8 feet in diameter, and posts that are generally an assembly. We worked on this concept with GDLS and delivered a magnesium turret basket component, actually 3 of them. This is one. This 28-inch diameter component was fabricated in open atmosphere. We are the only additive process that can print magnesium. And magnesium is very important. GDLS commented that the only way this lightweighting application works is if there's no scrap. And the only way to have no scrap is to use an additive solution. We are now engaged with both BAE and GDLS and are looking at the RA2 turret basket next. This method of lightweighting is well known to us from our aerospace customers. By using stringers or stiffeners, you can lightweight any component and bring a thick plate down to a thin plate with minimal weight. However, traditional manufacturing requires starting with a thick plate, say 2-3 inches thick, and machining out 80 to 90% sometimes of the material away. With MELD, you can add these stringers or these rib stiffeners to a thin plate. So in addition to saving the material, you're saving the cost of starting with thick plate, but I think most importantly to us all, you're saving the lead time. The thicker your original plate, the longer it takes to get, and certainly the more expensive it is. This concept came from AMP's Technology Advisory Board meeting, of which we are a member. So to demonstrate this capability, we fabricated this panel, actually this panel off to the side. You can see a very large component here with these stringers added, and you're welcome to come up and have a look. There's little to no distortion, again, because we're not melting, so it's a low heat process. We're putting low stress, low distortion into the part. In terms of next steps, we have submitted a proposal to AMP for lightweighting aluminum concepts, which should be announced any day. This same concept applies to manufacturing components in general. For example, one of our defense primes just asked us to quote putting very small features on a plate. There's a plate for a control surface that has basically a hump on either side. That requires twice the amount of plate for the maximum thickness of most of the part. So by being able to add those features with MELD, they've saved or will save 6,000 pounds of titanium, as well as the material cost, as well as the machining time, as well as the machining cost. Our next demonstration was to demonstrate repair capability to field new alloys. So there's so much activity happening in alloy development at this time, but these new lightweight, high-strength alloys, particularly aluminum alloys, 2000, 7000 series, are not friendly for welding processes. If you have a solid-state process, then you can repair them. And with MELD, we've shown that we can repair ballistics damage and crack damage. And in terms of transition, we are preparing our SBIR Phase 2 for this activity with the Ground Vehicle Systems Center to focus on the engineering work to deliver this capability on a robotic arm. On our own, we demonstrated the repair of ballistics damage. So these plates pictured are in front of you. You're welcome to come up, have a look, turn them around. The point is you can put metal on metal and not distort the product that you are intending to repair. So this can be done in the factory, this can be done in the depot. But what's most exciting about this open atmosphere process is that it can be done at the point of need. We brought the machine here for you today to see its scale. This is our baby machine. We want you to see the user interface. There's one touch screen. This is not a panel of knobs and buttons. We're not at NASA. We don't need PhDs to run the machine. It's very safe. It's very easy to use. So far, it's very hard to break. It's low power. It can be run off the generators with a mobile machining center. It's open air, so you're not bringing gases. It can use solid metal, so you're not bringing explosive powdered metal. It needs little to no surface preparation. It's very easy to implement at the point of need, put assets back in the field. So that's all great, but in an extreme case, you have assets that need repair. You have the capability, maybe you don't have the material. So what's most exciting is that this machine can accept almost any metal you give it. And this was demonstrated recently with ARL. They sent us a scrap material, they sent these plates, asked us, can you deposit material in this simulated crack? And we did. And that's here. They did a CT scan, which is the image you see in the middle. You see full density there. So this was considered a successful repair by ARL. What's most exciting about this is what was in that material they sent us. Literally, battlefield scrap. The next demonstration focuses on the ability to improve survival. Again, vehicle protection, and again, enabling advanced materials. This came directly from customer discovery. We were asked, can you put this ceramic tile in a metal case? We said, okay, we've never seen these before. And they're these. So we got introduced by the Army to Corstech, who produces them. They're a current supplier of ground vehicle ceramic armor components and armor. We did put the armor in metal, and that's also here. Then they said, okay, that's nice. Can you shoot that? And we said, oh, okay, well, in that case, we need a fully enclosed tile. So we'll just fabricate one really quickly and shoot it ourselves and see what's possible. And we did that. And you can see the projectile fall from in front of the tile. And so that seemed good, but I took these pictures and sent them off and said, does this look right? And they said, yes, this is exactly what we're looking for. We're looking for ejection of the projectile, and in the bottom right, you see the back side of the tile, which has no through hole from the projectile. So of course, ARL asked, can we have one? And so we made one for them to test, and they said, okay, not us, but send it to Hardwire, who is already an existing supplier of armor to the Army. And they were very helpful in helping us understand requirements and manufacturing guidance. So we did that. And they said at this time, with what we're doing, which is basically very much a proof of concept, just one tile instead of a panel, and doing it in aluminum, which is economical to test in, what we're really after is containment. So does the whole thing blow up or just this ceramic? And you can see the ceramic is what we lose, but we had complete containment. And this is just in aluminum. So the goal is titanium. This is something that the Army has known for a long time. They're very excited about, and we feel the cost savings and the weight targets only get better as you move up into large multi-tile panels like the one to my left. Titanium is already better off for going through the MELD process. This comes back to grain refinement, which I'd be happy to explain at a later date. And this is also something that has come out of recent desires from the AMP team of both Army and industry. So I'd like to change gears a little bit and talk about a demonstration of the priority for long-range precision fires, specifically the value that can be added for propulsion for extended long-range missiles and advanced warheads for cluster munitions. We've lowered the cost, and these comments come directly from our defense customers. These are much larger scale cylinders that are missile bodies. This is a small scale, just demonstration. This gets built one pass at a time with the MELD machine. And performance of ballistics can be improved with MELD. So some other things that we've done or are doing that I think are of value for you to know about. We currently have an ongoing project with CERTIP to characterize putting scrap in the machine and building parts. So this work is to understand how good is the part, let's say if the chips are still dirty from lubrication and machining fluids. We are working with the Canadian Air Authority to certify a repair process for this magnesium bell helicopter case gearbox housing, and this also is in magnesium, so very difficult, no other repair process. We are expecting any day now to have a phase 2 awarded from NAVSEA, which will be focused on integration and evaluation of MELD for a variety of naval materials for both build and repair, and we'll have our larger machine, the K2 model, housed at our facility for 2 years to do that work. 5 shipyards have come together to propose a project for replacing really large steel castings with MELD to NSRP. We were just awarded an STTR from ERDIC for bridge and rail repair for civil infrastructure. A little bit about the team. I'm the CEO and owner of MELD. I've been working on this technology for 12 years. I'm very excited that just last year we came to market. We got to the point where the hardware and the software could be utilized repeatedly by others. My team consists of scientists, engineers, electronics, hardware, software, production, and technicians. And together we have won a number of awards since we came to market in January of 2018. Further, this team has been awarded 14 patents on this technology, and also just in the last month we received our trademark for MELD. So that's us and what we're capable of. We wanted to ask some potential soldiers who might use the technology to come try it out. And so we recruited some cadets from Virginia Tech, and here's their experience.
Described as a large metal 3D printer.
3D printer for metal.
I would just describe it as a 3D printer that essentially spun a piece of metal to the point where the friction made it so that it could stack metal on top of metal and print anything you want. I would say it was very easy to use. When I came in here with little to no expectations, I was still blown away.
It's easy to use, buttons are pretty self-explanatory, so once you watch it done once, you're pretty much good to go the second time around.
I think this would be a huge benefit to the military.
I can easily see soldiers using this after minimal training.
The magnitude was large, but actually applying it in use, I'd say it was a lot easier than I imagined.
MELD is a solid-state additive manufacturing process that is performed in the open atmosphere, which enables it to be used for very large structures. It has a very high deposition rate. It's compatible with any metal, and we see a lot of interest, especially for large structural components in aluminums that are just not available currently in other metal additive processes or even in repair technologies. So the Army would like to utilize these high-strength aluminum alloys in the design of the structural components of the vehicles, whether it be a frame, a hull, other critical components. However, while they can potentially make some of these parts with conventional machining, forgings, they do not currently have a way to repair or do maintenance in the battlefield. I think the greatest value this offers the Army is the flexibility. They currently do not have a means to repair these high-strength aluminum alloys, which is why they aren't currently used. They don't have a way to repair them. So this turns a switch on to improve the design, to lightweight the vehicle, to improve readiness, to improve safety, to improve performance in the vehicles for the warfighter, but they just can't use them unless they have a way to sustain them. And this is a viable, commercially ready way to sustain these materials. So the Army, some years ago, several decades ago, identified the best way to manufacture passive armor would be to encapsulate ceramic tiles in metal. However, they were not able to make it financially viable. I was told that they were basically given the option: you can buy a new vehicle or you can buy armor for the vehicle. The cost was pretty extreme. If you consider what the armor looks like, is a ceramic tile may have this form. It's a ceramic, it's got very good performance in ballistics. They approached us and said, hey, we have an idea. Is this something you can do? So we took the tile, we looked at it, and we said, okay, we know we can print, we can additive manufacture with titanium, we can additive manufacture with aluminum. And we have certainly encapsulated or embedded things within the metal while we printed. And we didn't see a reason we couldn't do this. So we set out, we put these tiles on the machine, and we're able to encapsulate it. So a tile like this is within this aluminum block here. And so this is very exciting. So we've taken these now to the range and are doing testing to see just how good the performance is. And from there we'll be able to iterate. But the vision is that now you have this really flexible means to manufacture armor in custom applications, custom geometries, specific to a vehicle, maybe specific to a mission, a requirement. So it's a very exciting opportunity, I think, for something they really want to be able to do. So this is a missile launcher rail, which sits underneath an aircraft, and this is what the missile attaches to beneath the aircraft. So as the plane's flying around, the missile sits in this section here, and over time, this part gets worn out. However, the price of the part has gone from $6,000 to $20,000. So now not only is it attractive, it's imperative that we find a way to fix this part and keep them in service longer. So we do a nice demonstration, demonstrate we can repair these parts and ship them back to the Air Force for their evaluation. So 5 years later, they come back to us and say, hey, we've been flying these parts for the last 5 years and they're performing very well.
I thought it was really impressive. One of the things that I'm most impressed with MELD is its deposition rate. So our specific project right now is one use case. It's using MELD as a repair technique in family infrastructure. However, MELD applies to many other different types of applications, even within civil infrastructure. In a military application, the military relies on transportation to get troops and equipment from one site to another, right? Without those, the troops cannot perform effectively. So they're going to rely on the infrastructure, meaning the roads and bridges, to get from one place to another. Without that infrastructure in place, they can't perform adequately, and they're left with fewer tools, improper equipment to perform a job, which is very critical.
I would say it's very innovative. I'd say it's futuristic in a way of like seeing the things they're able to come up with and their ideas for the future. I think it's going to be a better system moving forward of how to repair and build things. I think it's going to be safer and cleaner and more efficient. I think overall, that's the way that our military needs to lean, is having a way that we can be, I guess, more proactive with how we're doing things and wasting less resources and being able to like move things from place to place and able to drop any concept that we need to.
Oh, you could use this to, the first thing that pops into my mind is tanks that have been in combat and have bullet holes. You could fix them, just quicker process, quicker turnaround, cheaper, since you don't have to order a whole new plate to replace it with. You can just fill that little hole.
I'd say it's really exciting. You know, I describe it as almost a looking glass into what we're developing and how we're doing things, and really the future. Because I mean, equipment needs to be repaired all the time, and if we can come up with concepts like this and actually put it into mass, I guess usage nationwide, it'll be really helpful.
This is the component that some of those cadets manufactured in their afternoon with us. So they came in hours, learned the machine, and were making parts or doing repairs. In terms of transition, we are working on the having our equipment listed on the GSA schedule at this time. That would be Schedule 36, which includes additive manufacturing. And our letters of support for that effort came from ARL, Naval Surface Warfare Center, Carderock, and also NASA Marshall. Further, as I mentioned, we are members of AMP. We were asked to join specifically for the ability to receive OTA contracts through this organization. Obviously, we have a commercial presence, and not only machines, but parts and services, training, and something we call Discovery and Development Program can be offered today to anyone. We are working with a wide variety of industry. These are some of our defense partners, but our industry partners and customers span from consumer electronics to oil and gas. There's literally no industry that cannot benefit from additive manufacturing, and certainly from additive manufacturing for metal. Today we offer two versions of our machines, which are 3-axis style, and we are happy to announce with our latest customer that those are located globally in research centers and universities, and I'm very excited to announce our first sale into industry with the machine just this month. So we stand ready to support your directive to enable readiness and modernization through advanced manufacturing, and we would like to help you bring a dragon to the fight. This is my life's work. I'm very excited to see it happen, and I'd be happy to answer any questions you have at this time. And also, I'd like to invite you up to see the things or the machine.
I was wondering about the surface temperature when you're doing the application of magnesium. When you were building the magnesium part, did you measure the temperature of the material?
In all cases, the temperature of the deposited material is going to range between 60 and 80% of the melt temperature. That's a good rule of thumb. There are opportunities to control temperature if there's some desire to do that. And we do have the ability to control ductility over strength, for example, in that way, if needed. But in all cases, you're going to see about wrought properties from the melded material.
A few questions. So, difference in strength between removing material versus adding the material. So when you showed the picture of the door and you talked about thinning out material, instead of doing that, taking a thin piece and adding material, what's the difference in strength in adding it versus taking away from a solid piece of metal?
With the MELD process, they're approximately the same. So with MELD, we see about wrought properties, sometimes a little bit better, sometimes a lot better, depends on the material and if it's heat treatable. This is I would say the singular process for metals. where you can build up a part. This part that I've built up, if you put it beside a part that you machine down, your performance would be about equivalent. Now, there'll be times where I would say the melded material will be even better, but I think the blanket answer is they're about the same.
Has been operated in field-type conditions, 130 degrees plus, sandy, dusty environments?
I think that's a fantastic question. The closest thing we've gotten to a field operation is to invite some college cadets in and see what they can do. But this equipment, the reason the equipment is here for you to see is that it basically is CNC equipment. So the equipment you're used to having in a machine shop in the field is this equipment. And if I can put machine chips in this machine and make a viable part, lubricant and all, a little sand isn't going to make a difference.
And then I saw that it's going to be available for purchase on GSA. What's the plan for training and or maintenance of that equipment through the purchase of it?
So we offer the training today as a standalone service to anyone. You're welcome to come today. Part of our Navy contract is to walk through that training with sailors and see how we can enhance it. And then the maintenance is not, it's the same as maintenance on your CNC, honestly. It's extraordinarily simple. I mean, I think the elegance of the solution is its simplicity.
Hi. Could you talk a little bit about how the MELD process compares to some other additive manufacturing technologies like cold spray?
Absolutely. Cold spray is one of my other favorite processes because it's also solid state. Cold spray requires powdered metal. MELD can use powder, solid, or chips, and cold spray requires gas so that it can be delivered. Cold spray has a lot of flexibility. It's basically wherever you could take a garden hose to, you could take the cold spray solution to, but it does still see voids and porosity at the interface, as well as the added material, and it's not a technology that you would build parts with. I think it's an excellent repair technology.
Okay. And then just in terms of deposition rate, about, as an example, how long did it take to build that the missile housing there?
Yeah, so deposition rate, we have about 20 pounds per hour. And actually, I can show you, these are the materials we've processed ourselves and some deposition rates. When you're in aluminum and magnesium, we can put down a lot of material. When you get up into steel, air mets, we're going to go a bit slower, but still overall, this is a very scalable, well-suited to make big things with a lot of metal.
Can you, in the video, it almost looked like with the ceramic tiles that you were kind of printing in place, but I'm not sure that that's the right impression. I think what you do is you print the matrix, a little cleanup machining, and then put it in place. Is that, can you just clarify?
Yeah, absolutely. For our demonstration articles, we started with very thin plate and built up the walls, and then placed a top cover and sealed it with the MELD process. In this way, you start with a minimum amount of plate material. However, in this configuration, what we'd like to explore, if we have the opportunity with ARL, is to print the matrix in place. So I could explain more later, but you can actually move material down into some cavities with this process, and we've done that effectively with the missile launcher rail repair, actually. So how we optimize manufacturing, there are a couple things we can try.
So I have to assume your 14 patents are on the process, right?
Process, hardware, software.
Okay, so then I'm confused on how you have this in a distribution system. Are you licensing the technology to other people to utilize it? Are you selling the machines? How do you actually foresee it being distributed?
Today we sell machines, and we are happy to license. So you don't have to purchase a machine from us. If you have your own, this technology is so well suited for large things that some of our aerospace customers, you know, if you're talking about spacecraft components, dome, you're not going to make it with this machine. In which case, you probably have your large-scale machine fabricator of choice, and in that case, we'll support it with integration and a license, but you don't have to buy the equipment from us.
To that point, I was going to ask how scalable is the core technology? Can it be scaled up to a larger machining capability that would support something like you just described?
So the components that these 5 shipyards are interested in are the full-scale structures that are at the front of the ship. So they're 30 feet more in height, space, aerospace, yeah, so not little widgets, but big stuff.
Okay. And do you produce all your machines in-house?
Yes.
Okay. And how many of the machines can you put out, say, in a month time frame? How long does it take you actually to fabricate a machine?
Actually, we've really done a great job over the years of getting down to modularity of components. And as I said, this is a very simple CNC style frame. It's running off G code, so there's not a lot of custom components inside of it. So I think we can turn them as quickly as in 3 months from order at this point.
And
Great, thank you.
Oh, thank you all.
That was fabulous. Thank you so much. I had to cut you off.